Machine learning is employed to develop an efficient algorithm for real-time equitable load shedding in power systems. The proposed approach tackles the optimization-based load shedding problem, which involves complex constraints, to ensure fairness and eliminate bias against specific regions. The optimization problem is formulated to minimize total generation costs and load shedding, while considering various features associated with each node or region to promote equity. The decision variables include phase angles, generation, line flow, and load shedding, with operational limits and constraints to ensure fairness and prevent biased decisions. The optimization problem is a quadratic program that can be efficiently solved using optimization solvers. However, to meet the extremely time-critical requirements of load shedding, a machine learning algorithm is proposed to accurately determine the binding or non-binding status of each inequality constraint based on different inputs. By analyzing the optimality conditions, the optimal solutions to the original problem can be obtained by solving a set of linear equations, enabling real-time computation of load shedding decisions. The equitable load shedding problem is formulated as a quadratic program, with the objective of minimizing total generation costs and load shedding. The decision variables are subject to constraints, including DC power flow, nodal power balance, operational limits, and equity constraints to promote fairness. The equity constraints include limiting the discrepancy in load shedding between any pair of nodes and ensuring that the load shedding decisions are independent of various features associated with each node. The machine learning algorithm is proposed to learn the binding patterns of the constraints, which can be used to establish a linear system and facilitate real-time computation of load shedding decisions. The approach is demonstrated on both a small system and a realistic RTS-GMLC system, showcasing its validity and computational efficiency. The proposed algorithm has the potential to provide timely and effective load shedding decisions, while eliminating bias and promoting equity in power system operations. Here is a combined summary of pages 3 and 4 of the research paper. The load shedding problem is formulated as a quadratic programming (QP) problem, which can be cast in a generalized form with decision variables, constraints, and a cost function. By leveraging machine learning methods, the binding constraints can be effectively learned using input parameters, enabling real-time decision-making. The Karish-Kuhn-Tucker (KKT) conditions for the equality-constrained optimization problem are derived, and the solvability of the linear system is ensured by the non-singularity of the KKT matrix. A generalized neural network model is adopted to learn the binding constraints, with load inputs and binary outputs indicating the binding status of each constraint. The optimal dual solutions can also be utilized to determine the binding status via the complementary slackness condition. The neural network is represented by a set of equations with activation functions, and the binary cross-entropy loss function is used for binary classification tasks. However, the analysis assumes a known load vector, which may not be realistic in practice due to load uncertainty. To address this, risk measures like value at risk (VAR) and conditional value at risk (CVAR) are introduced to adjust load inputs to match different levels of risk. The CVAR is preferred over VAR as it is a more coherent risk measure and less dependent on the underlying distribution. The risk-averse load shedding approach uses the CVAR of the load distribution at each node, allowing for flexible adjustment of risk levels associated with each load. The collection of risk-averse load values can serve as the input to obtain the binding constraints. Furthermore, robust solutions can be pursued by using the maximum load values to ensure robustness against the worst-case scenario. The paper concludes with a numerical simulation using a 3-bus toy example and a 73-bus RTS-GMLC system with realistic datasets, demonstrating the effectiveness of the proposed approach in solving the equitable load shedding problem. The paper discusses a machine learning approach to solve the load shedding problem in power systems, aiming for real-time and equitable decision-making. It formulates the load shedding as an optimization problem, which can be simplified to solving a set of linear equations by learning the binding constraints. The approach is demonstrated using a 3-bus illustrative example and a more realistic RTS-GMLC system. The results show that the learning to optimize approach can significantly reduce computation time and improve prediction accuracy. The paper also discusses the importance of considering fairness in de-energization scheduling to mitigate wildfire ignition risk.